So welcome everyone to the COMSOC video seminar. This will be the last session for what I guess in most places would be called the academic year. In the Northern Hemisphere, we are going for a summer break. The rest of you, I don't know how you would call it, but we're going to have a couple of months without seminar. Somehow we will try to manage to do that. And I'll say it again later, but maybe let me say it already now once. So our plans for after this summer of the Northern Hemisphere is that we want to reduce the frequency a little bit of the seminar. So we have the feeling that now in some places, excluding, for example, the country that I'm in, but in many other countries, it's going somewhat better at the moment with the corona and all that, and that more people will have the chance to meet in person again. And so we don't want to compete with that all the time. So we thought it would be right to aim for a seminar once a month. And so we'll try that from September for a few months and see whether it feels appropriate to do that. And we had a long and heated discussion to figure out what's the best time of the month to do that. And we figured out it's the second Thursday of the month at 3 p.m. in Paris, 9 a.m. in New York. So the usual time of the day. We're moving back to Thursday, as we did at some point for a while last year. And we thought the first something of a month is not good because everybody will go for that. So we'll go for the second Thursday of the month. That will be the default meeting time, and I'm sure there will be exceptions to that for various reasons. But that's the plan for now. Then today we're going to have another wonderful session. We have two very interesting speakers. I will introduce the first one in a moment. I'll first explain a little bit how we do things here. So we have two speakers, 20 minutes each. There will be a break in the middle with the breakout rooms. So you will see when that happens, I'll put everyone in a randomly chosen breakout room. And if you want to, you can have a chat with a handful of people that will probably show up in your room for 10 minutes. And during the talks, if you have a question while the person is speaking, please put your question into the chat using this format that I've just put an example there. So you put in uppercase letters question, makes it easier to notice because people also go and answer some of these questions, or sometimes just, when they've noticed somebody in the audience they haven't seen for ages, they say hello or something like that. That's all very welcome, but to be able to find the questions is good if you mark them like that. And the speaker is unlikely to notice this during the talk. Maybe somebody else in the audience will be able to answer in case it's some kind of clarification question. And in any case, the person will be able to take up that question after the 20 minutes over. We have around 10 minutes for the Q&A after each talk. Okay, so Vincent has already shared his screen, I see. So let me briefly introduce our first speaker. Vincent Merlin is research professor in economics with the CNRS, based in Caen. He's doing all sorts of things in social choice theory, axiomatic things, also related to how often certain phenomena happen, like paradoxes or certain voting rules agreeing or disagreeing with each other, these kind of things. And what he's going to talk about today also fits a little bit into this latter category about how often certain problems occur in different ways of setting up an election. So Vincent, the floor is yours.
Thank you, Ulle. So as you all know, we heard the sad news on the 10th of June that Peter Fishburne passed away. And Peter Fishburne had made many contributions to economics, operation research, and social choice. And in social choice in particular, he made very deep and important contribution and the probability of specific election outcomes. So when Ulle asked me which topic to choose 2 weeks ago, I thought it would be good to pick a paper, to pick a set of works that deal with this line of research on the probability of election outcomes. So today, what I will present is a paper, and it's not a paper, it's a set of 2 kind of works. It's the probability of disputable outcomes under direct and indirect election. It's a bunch of 2 types of results. some old results that I have for years written with Jack Nagel, which have never been published, and some new results I'm currently doing with Théo Duchemin, who is a PhD student at the University of Caen. So let's go for the first. Okay. So we all know what motivated us is basically the US presidential election and the Electoral College. As you all know, the latest election were led to electoral dispute because Donald Trump clearly had won the election, which of course we all believe this is a false claim, but still he said that the result is Wisconsin, Pennsylvania, Georgia, and Arizona were close enough so that maybe some frauds could reverse the result of the election. So in this case, as you can see, if you look at the margin of the election in these states, it's true that in Arizona, Georgia, and Wisconsin, the margin was less than 1%. And perhaps what could have discovered hidden ballots or strange things so that the result could be reversed. So the problem with the Electoral College is that maybe it's sensitive to electoral disputes in the states, so that by disputing the result in specific states, some pivotal states, we can try to reverse the result. So 2020 was in some sense a close election because basically its result depended only about a bit more than 4,000 votes in Arizona, Georgia, and Wisconsin. And if you somehow manage to reverse those results, you can change the result of the elections. In 2016, well, the election was close too because Donald Trump won Pennsylvania, Michigan, and Wisconsin with less than 1%. But Hillary Clinton did not contest the result. But we had another problem here. We had what we call sometimes a referendum paradox or an election inversion, because Hillary Clinton got more votes than Donald Trump nationally. So here we had an election. We had an election inversion, but no legal dispute about the result. And of course, the case where we had a legal dispute and a paradox is 2000, when we had a legal dispute in Florida. And as you know, George Bush won this legal dispute in Florida, even though at the national level, Al Gore got more votes than George W. Bush. So the question is the probability of a disputable result under the Electoral College sufficiently greater to offset the higher cost of a national dispute? So this problem of electoral dispute, is it more likely in an Electoral College setting than if we were adopting a national popular vote, a direct vote? And this is, actually a hot debate in the US. So we were wondering whether which system, the national popular vote or the electoral system, would lead to electoral dispute or legal dispute about the result. In the older paper with Jack Nagel, we did several things. We looked at the past, and we did some kind of model with IAC to try to evaluate the merits of the two systems. Recently, there was a very nice paper by Geruzo and Spears in 2020, where they tackled the same question, but using micro simulation with actual electoral data. And they found that an electoral college was 40 times more likely to get to an electoral dispute than the national popular vote. So I won't discuss too much this paper, but there's also some work in this area at the moment. But for us, we will go back to a classical IAC model that I guess most of you know. So perhaps I would go very fast, but the first point we have to ask ourselves is what threshold for disputable election should we take at the local level or at the national level to state that an election is disputable? If you look at political science, usually most of the recount occurred when the threshold was on average 0.5. If you look 0.2, for example, this is what we look in political science. This is where usually actual recurrence occurred in the US. If you look at the state legal triggers, they are usually 0.5 or 1%. So this is basically the benchmark we can play with at the local level. Of course, there is no legal trigger for a national popular vote at the moment. And due to the law of large number, we can expect that the national trigger will be smaller because, of course, we're in a state where we may have 1 million voters, though nationwide we may have 150 million voters. So we can use smaller triggers like 0.1, 0.2, and 0.3. If we look at this and at history, what do we find? We find that the Electoral College was disputable 8 times over history, twice with a threshold of 0.2% in 2000, it was Florida, and also in 1884. 5 cases, we have 3 more cases if we go to 0.5, and we have 8 cases if we allow, basically consider that there could be a dispute with a 1% threshold at the local level. And K is a number of states you have to flip, which were below this threshold to flip the result. If we look at the national popular vote, there are only 3 cases where the election were really close nationwide. And you see this. So if we mix that, can we say in history that the national popular vote is more disputable than the electorate? Well, this depends. If you take 0.2 at the local level and 0.2 at the national level, we have 2 cases, they are equally likely to lead to a legal dispute. Of course, if you take this very strict limit for the national scale, 0.1%, on this larger one at the local level, you have 1 to 8. So basically, if we look at history, we say that an electoral college is from 1 to 8 times more frequent to be disputable than a national popular vote. Now let's move to a model and our probability computation. So here we're not doing like Geruzo, we basically use the actual data and make micro simulation of the current electoral model. With that, we want to go to a classical ahistoric model, a classical impartial model, and we will go for impartial anonymous culture. So we took here impartial anonymous culture and not the classical impartial culture. The impartial culture, as you may know, is just flipping a coin. In each state, everybody flips a coin. So if you use impartial culture, everything is tied everywhere. So everything is disputable with probability 1 everywhere. So it's not really, it's the first model that was used in social choice literature to analyze the probability of paradox, but it's completely irrelevant in our context because we will model the two-party competition in each state, and it will just lead everything is disputable all the time, which is not the case. The IAC model is much more nice in that case because it assumes that all the results from 0 vote for party A to all the votes for party A are equally likely. So basically, party A can get 10%, 30%, 50%, 60%, 70%. All these results are equally likely, and it's much more like what we see in reality. Of course, if you look at US data, it's not the 0% to 100% range and variation among Democrats and Republicans. But if you basically shrink your range by 2, going that all the results are between 25% for Democrat to 75% for Democrat, it's almost what we observe in reality. So IAC or some kind of variation of IAC could be rather realistic in the first approach to model the US Electoral College. So what we would do, I will first show you some results for 3 states. I will then go for a formula for a large number of states, and then we will move to the more recent result I'm currently working on with Theo Buchmann. So first, we will, with a class of generality, in the first part, we will assume that all states have equal size, and the state of each state is 1. You can say it's 1 million voters for each state. So there are 2 parties, A and B, no abstention is allowed. And as we are using the IAC assumption, we will draw a result for party A in between 0 and 1 in each state. So we just do random draws between 0 and 1 in each state. One key assumption here is that these votes are independent. That is, the result in the first state is independent from the result in the second state, which is independent from the result in the third state. So if we just have a look at what is the problem for 3 states, the problem is basically that we just draw randomly points in a cube, and we'll see whether we fit in the zone where there's a paradox or a problem or not. So basically here, if you look at the problem we have for 3 states, it's just a problem of we will just having to pick 3 points in this cube. For example, here, y is basically, if you look here, point 1 is basically the case where party B got 50.5 on 100% of the vote. So he wins all the states. But the problem is basically point Z, for example, the point Z, B got 49.5% in the first state, 100% of the vote in the second state, and 0% of the votes in the third state. So A as a majority of state and is the winner, but of course it's tempting for party B to have a legal dispute in the first state to say, no, we're not in ABA, we're in BBA, and I'm the winner. Okay, so we are looking basically at the probability we are close to the kind of boundaries. Yes, for the moment, all the states have the same population for the moment. So if we do that, we can have the first result. The probability of an electoral college dispute with 3 states, P3, EC, for a trigger T. So this T is the absolute threshold for disputability. We can compute, and this is basically 3/2 times T minus a term which is in power T. So if you think that T is 1%, that is, you have a dispute if there's less than 1% between the 2 parties, this means that you will have a probability of a dispute in the electorate would be 1.5%. We can do the same for the national popular vote. Here, there's a dispute if, on average, we have 3 states, so the population is 3 million. So you have a dispute if you're close to 1.5 million. So if the result is close to this result, to this hexagon, where each party goes close to 1.5 million votes. So here Z is contestable, but not Y, and you just compute the volume, which has a distance epsilon of this hexagon, and you get also a formula. So we get 3/4 for T minus a term in the power 3. So basically, only the first term is important. So here, if you think it's a 0.1 also as a trigger, you say, oh, it's 0.25, the probability of a paradox, so it's less. But no, it's not less, because now the population is bigger. So if you want to have a 1% trigger, 1% of the population, you have to multiply this by 3 to have a 1%. So if we consider a 1% threshold in both cases, then here it's 2.25. So the probability in the 3-state case is higher with the national popular vote than with the electoral college. So if we consider a large number of states, we can have an estimation of the probability of the dispute for the electoral college with n state and a trigger T, and it's something which is square root of 2n over pi times T with some approximation. And we can do the same for the direct vote, and it's something also which is T times square root of 6 pi n over pi n. So we have some kind of asymptotic limits to the probability of dispute in this toy model. So when we look at that, if you look here, the probability of the electoral college for a trigger T, for example, 1%, this is increasing with the number of states. So if you take something like 51 states, should be about more than 10% of the case. We should have a kind of a paradoxical result. For the national result, it's a bit difficult to say something because it depends how the national trigger evolves. If it's still the same absolute number of votes that the Electoral College, the same T, of course, the probability of being in 10,000 votes of difference at the national level is going to crash as the number of states goes. So, of course, this probability goes down. If we assume that the national trigger goes with the square root of the number of states, then the probability remains the same. So progressively, the situation becomes less favorable to the Electoral College. If we have the same percentage of votes locally and nationally, basically the two curves evolve in the same way. So basically, the discussion depends on which trigger we use for a recount locally and nationally. I think the most likely situation is the one where the national, for example, the state trigger, for example, is 1% T, and the national trigger evolves as a square root of n times T. Then progressively, it will be more likely for the Electoral College to lead to disputed outcomes. Yeah, I'm already running out of time, so I will skip a few things. I will just go basically to the table we discussed in the beginning, in the introduction. If we look at what we observe in the data, that is, for example, the probability that we have 1% threshold locally and a 0.4 up, and a 0.4 trigger nationally, we found 3 cases overhead. That is, it's 2.6 much more dispute in the Electoral College than the national popular vote, and our toy model is 1.44. So our toy model is not in red, is not that far from what we observed in reality, and perhaps more than the micro simulation that were put forward by Guéruzo and his co-author. Just because I have 1 or 2 minutes left. So at the moment, I'm working with my student Théo Duchemin on one limit of our first paper, is that, of course, in reality, states don't have the same population. And we know from some results on election inversions that the existence of 2 big states among a notion of small states can drastically increase the probability of election inversion. So we have started with Theo to examine what's going on with different population in the states. So at the moment, it's very preliminary. What we can report now are just simulation for 3 states, but we hope to go up to 50, 51 states, of course, at some point. So with 3 states with population N1, N2, N3, and N1 superior to N2, superior to N3, of course, each state then control EI electors, and we assume that the same number, the electors controlled by the setup, strictly proportional to the population with the winner takes all principle. Then we have the result of first simulation. Well, it's not a lot at the moment, but the probability of an electoral college, well, we come back to what we found, of course, theoretically, with 1% threshold locally. Of course, here, this is a case where I've got basically 2 very small states and 1 state, which is a dictator. So of course, we come back to everything is governed by the state, which is a dictator, and the result of the probability of a dispute is 1%. Basically, it's equal to the probability of the trigger. So, well, it's just a first step. And if we go for the probability of the national dispute, well, we recover by our simulation, of course, but all the states are equal to the same probability. Of course, here everything is governed by the largest state, and as we can see, also the probability can rise a bit when we have 2 big states and 1 small state. But again, this is the first step. We are planning to launch this summer simulation with a bigger number of states, and we hope that by the end of summer we will be able to tell you what is the influence of diverse representation of the population across tests on the probability of a dispute. Okay, I would just keep that. Also have, of course, conditional. We can do, of course, conditional probability, and we will do that also in the general case, but I will stop that. So our plan over the summer is to have extension to more than 3 states. Okay, so maybe I will stop here. In conclusion, what can I say? Surely an electoral college in a simple IAC model is more disputable than a national popular vote, but perhaps not as much as was feared, and perhaps not as much as was stated by Geruzo and Stern in their paper with making micro simulation. Thank you very much, and I'm ready to hear your question.
Thank you very much, Vincent. I would like to suggest that we unmute ourselves for a round of applause. And we do have time for questions. I'm going to start with Bill, who typed something into the chat. You want
this is a good point.
Do you want to, Bill, do you want to ask in person, or is it clear like this? I don't know.
Yes, I have some intuition that I'm not sure I can make precise. It may be based on assuming something other than IAC, that we would expect, for example, suppose we had a epistemic situation in which there was a correct number of people who voted for one party versus another. It was close to half, but it wasn't equal to a half, and then we had noise. I would expect as the number of voters goes up, we expect the percentage error to go down, which would suggest using a lower threshold T for the national public vote than for the state vote. Whereas it seems to me you're going the other direction. Is that correct, Vincent?
I'm not sure to understand your question, but the idea in this paper is basically a dispute are due to errors, not frauds. So basically, there could be an error because we did not count 10,000 absentee ballots somewhere or something like that. So if we assume that the error are randoms, as there are more states, there are more random terms in each state, and the sum of these random terms will follow a normal law, which variance goes as the square root of n. So basically, the law of errors nationally will not grow as fast as the number of states. This is basically our argument, one argument. If the errors are independent, of course, from states to states.
What does that say about the threshold you use nationally versus for a national public vote versus for a state-by-state vote?
We think that it should be lower in terms of percentage nationally than locally.
Okay.
This is basically
what I thought. That's what I thought as well. Thank you.
Yeah. It should go basically. I think the most credible answer would be that if there is a local threshold T in terms of absolute number of votes, 10,000 votes, then nationally it should go a square root of n times T. Okay.
He says yes. He's muted, but he says yes. Okay, Franz, let's go next with you.
Yes, thank you, Vincent. If I take a vote in a particular state, and let's suppose that the Democrats win, according to the counting, win by 51%. Now, is that, one might ask, is that a sufficiently strong outcome for us to be sure that the true outcome is that the Democrats win? And it seems to me that this very much depends on whether we think that false counting occurs by mistake or by fraud.
Of course.
And if it's by mistake, then I guess by the law of large numbers, that should be a very, very strong probability that Democrats have won. But the claim of Trump is, of course, that there has been election fraud. And then even 55% is not much of a, doesn't give much of a certainty. Do you have an idea on how to model fraud, election fraud, and the probability of fraud being successful?
I fear not. I fear not. And the only way to know a model would say basically we're not taking a threshold of 5%, but a threshold of 10%. And then anything is contestable. But
yeah.
in Trump's mind, everything is, every result where he does not win is contestable. That's the problem. But technically, Hillary Clinton has exactly could have said exactly the same thing as Trump in 2016. The margin was not as big for Trump in the three key states in 2016 for Hillary and for Trump, but he conceded graciously.
Yes.
So of course our model cannot do anything. I fear our results. Cannot do anything against Trump, except that maybe it means that every result in the future will be contested by anybody.
I mean, I guess you have to abandon independence for a start, because fraud is not going to be independent.
One thing, I didn't look a lot at the paper by Geruzo and its technicalities. It's something I should do over the summer. But if you think of IAC will give you some, especially in the case where all states have equal size, it's just give you a bunch of results from one party got 55% in one state, one other with. So it just spreads the result across the state uniformly. So it's quite realistic in some sense, because if you think of US, Wyoming is 66% Trump, and California is 66% Biden. So there are also this kind of results in reality. So I lost my mind. Sorry. I think I lost my mind. Sorry.
Good opportunity to move on to the next question. So we have several. Let's go on with Peter. Do you want to ask yourself?
Can we have a press of the main paper? I have a paper I never published. I can send to people who wish to. Okay.
Okay, but
the paper.
So that, I think so. First of all, that one, the question by Caldita, I think, was a question about the references to the other people's papers. So maybe you can type that into the chat afterwards.
Geruzo and Spears, Michael Geruzo and Dean Spears. If you type Michael Geruzo and Dean Spears, their paper are on their website.
But do we know how to spell their names now that you?
Michael Geruzo. If you look at Michael Geruzo, you will go to his webpage and all his papers are there.
Okay, somebody will find it and will put the link there, please. Okay, Peter, you have a question.
Yes, it's about your model assumption that basically within a state all outcomes are as likely. I think the actual situation is that there is some sort of national average and that the various states fluctuate a little bit around it. So how about a model where you stipulate a national average and take a Gaussian around it? And that determines the state outcome and indirectly, therefore, the Electoral College.
Okay, I'm not sure to have understood. You mean if there's a bias in for one party, you mean? For example?
The fact is that if there would be a serious bias in the system with majority takes all, it would also mean that one party always win. The only reason is that why elections remain interesting, that on the national scale, the bias is rather small, that you see from the closeness of the national outcome. But the disturbing fact is that due to the winner takes all character at the state level, small state fluctuations lead to major fluctuations in the electoral outcome. And I'm curious whether you can incorporate that in your model by assuming that the state outcome is basically determined by a Gaussian distribution centered around the national average.
Okay. Okay, but again, some kind of Gaussian distribution around the national average is basically it's basically a kind of IC model, and the impartial culture model gives basically, if the Gaussian is too peaked, then you will have basically everything is disputable with probability 1. As for the kind of using Gaussian, which is sufficiently relatively high variance of the result, yes, we could do that with simulation. There's no problem. It's just that it should not, the Gaussian should not be too peaked so that on average everything is contestable.
Okay, final question from Luis, please.
Okay.
Luis, yeah, you can speak. No, now you cannot speak anymore.
Yeah. Sorry, I did not make any question.
Ah, I thought you put a Q in there, and that meant like.
Yeah. Well, okay. That's
question.
but even okay. Just since you contacted me, okay. A couple of things from a European point of view. How much of this problem will be solved if instead of using the winner take it all in assigning the electoral votes, we go to a proportional system of assignment of the electoral votes?
I'm not sure it could solve the problem, because in case of a closed national election in the Electoral College, then every marginal seat in every state could be contestable. That is, grabbing a state, one seat in California proportionally could be as important to grab one electoral college in Texas. So I would say that each marginal seat in each state will become, if the distribution of the electors would be proportional, I feel that would lead to the fact that basically each marginal seat in each state would be contestable. So that could be a terrible option in the current state of the US politics. You see my point?
Well, I understand what you say, but on the other hand, part of the problem is that with 51% of the votes, you get all the electoral votes. So it's a big move. For a very small move of the vote, you have a big move in the result.
Yes.
Okay. So that's what you, at least in part, could solve that way. But well, I do not know really. And I have another question.
If it's very quick, and if the answer is very quick,
the very
then I
last
will allow it.
question. That's the last question. Okay, I saw in your slides that if you increase the number of states, the likelihood of a dispute also increases.
Yes.
Okay, but I would have expected just right the opposite, because maybe you have a higher likelihood of disputing one state, but maybe the overall, I would have expected that there will be less disputes in the sense that, okay, but changing the result in this one state does not change anything.
Okay, maybe there's a trick.
I mean?
Maybe there's a trick in our model. Okay, maybe there's a trick. There's a trick hidden in the model that I did not tell you. Because we draw randomly across states, we draw the result independently from state to state, we're generating close election in the Electoral College. So the likelihood was we end up with, for example, 25 states for one, 25 states for the other, progressively will grow up as the number of states increases. And then any state becomes pivotal. So basically, what we see in the model is the higher the number of states we ask, the higher the probability of national election are close, and the higher the probability of the state is pivotal. That's the hidden part of the model that I did not reveal to you. That explains why that's it.
That's all. That's all. Thank you.
Okay, we have to stop here. Thank you very much once more to Vincent. I'm going to stop the recording for now. All right, welcome back. It's my pleasure to introduce you to our second speaker for today, Nick Mattei. Nick is assistant professor of computer science at Tulane University, New Orleans. He's also has been working on all sorts of different things. So one thing that many of you will be familiar with is his work on Preflip, on the online library of preferences that many of us use in our research. Also been working on other things like expressive preferences with CP-nets and how do you do voting in these situations, and also some things about more towards the behavioral side. So how do people actually, what preferences do they actually have? And I believe also today's talk is going a bit in that direction. So Nick, the floor is yours.
All right, thanks a lot, Ulle. Thanks for organizing this whole thing for the last 2 years and keeping us all connected through the whole thing. It's been really nice, actually, even though I haven't turned up probably as much as I should have. So today I'm going to talk about some work that Jael did as part of her PhD thesis. So just to full disclosure, Jael did like 90% of the work in this. I'm just taking all the credit here at the seminar. But we're talking about modeling voters in multi-winner approval voting. And so this is joint work with Jael, Jason Harmon from Louisiana State University, and of course Brent, who's now at the University of West Florida. But most of this was done while Jael was still a PhD student here at Tulane, and Brent was still here as well. We have 2 papers that I'm going to talk about kind of together. One was at AMAS in 2020, and one was at AAAI earlier this year. So the general pitch, which I don't need to make for most of the people in this group, is that we have to make a lot of collective decisions, and we want to use math and computer science and data and stuff to make those decisions better. A big thing, of course, that Ulle alluded to that I'm super into is making sure that the models that we build are inspired by the data as it really exists, right? So going out, doing behavioral experiments, collecting data, verifying some of the theory aspects of the things that we do in social choice with data that comes from humans, or at least actual decision makers. I guess they don't have to be human. They could be rats or something, I'm not sure. And so in this paper, we performed a real world experiment to understand how agents make decisions in multi-winner approval voting. And so I'm going to do kind of 2 bits of the talk. One is, going through that data and just giving you an idea of what we saw. And the second one, which is more of the AAAI paper, is using that data to develop a novel model of how humans make decisions heuristically in these multi-winner approval settings. So there's going to be kind of 2 parts to this. So formally, we're doing multi-winner approval voting. So given a voting rule R and a set of candidates of size M, we've got a set of approval ballots, which are just 1 or 0, yes or no. And we want to find some committee or group size of K. And so the sort of computational question, right? If this was more of a computational paper, would be, what is the winning set out of the set of candidates? And so standard, vanilla approval voting, individuals can vote for multiple options, so very much like a doodle poll. And it's pretty simple to understand. And so in single approval voting, you can it's basically plurality, but you show approval for more than one candidate. In multi-winner, we're going to take the top K candidates. So we're going to add up all the approvals that each candidate receives, and we're going to take the top K with the most approvals. And so there's actually a whole handbook on approval voting. I've done several bits of work in this over the years with people that are on this chat. And there's some nice funny quotes that I went back to a really old talk and pulled out. So in the single winner case, AV is nice because it's simple, it's propensity to elect Condorcet winners when they exist, it's robustness manipulation, and it's monotonicity. This is from the handbook on approval voting. And for dichotomous preference, approval voting is actually strategy proof. But in the multi-winner case, it's really not as clean. Because there's this question of what counts as an honest or sincere or truthful ballot, because there's multiple ways that one could imagine that you can express your preference in this multi-winner approval voting. And so what I mean by that is let's say we have a set of candidates, A, B, C, D, and E, and I've got some utility for these candidates, right? 0.05, 0.1, 0.01, 0.25, and 0. And so Brahms in 1982 defined a sincere ballot in multi-winner approval voting as a ballot where you approve of a candidate if and only if you approve of all candidates that are more preferred than that candidate. And I think, Ulle, you used this definition in a couple of papers for a while as well, trying to define what are sincere ballots. And so in multi-winner approval voting, there's actually a bunch of different ones you could do. So D, BD, ABD, ABCD, and even the full set ABCDE are all sincere ballots according to this definition. But you couldn't select, say, just B because you, in theory, prefer D a little bit more. And so one of the things that we do in this work is Jael and Jason are both psychologists, or Jason's a psychologist at Louisiana State, and Jael was very into human decision-making. So they mapped a lot of these different heuristics that people use onto this literature from psychology about, sort of heuristic decision-making and things like that. So that's one of the contributions to the paper. And so you could think about a couple of different heuristics that one could use in this setting, right? So one would be complete, right, which is where you vote for all candidates that you have positive utility for. You could do a take the X best, which is sort of a heuristic-y version of a sincere ballot, right? Because if you're taking the one best, right, the candidate that I have the most preference for, that's a sincere ballot. If I take the two best, that's still a sincere ballot. So it gets kind of this tension from strategy proofness and things like that. So these are the two kind of heuristics that we're going to focus on. And then from the literature, there's these attainable utility heuristics, which we'll talk about in the second part of the talk. And this attainable utility with threshold, which is the one that we developed as part of this series of research. So this is the kind of general setup of multi-winner approval voting and why we're interested, because there's a lot of different things that you could do in this setting that are still kind of sincere or truthful for some definitions of sincere and truthful. All right, so what did we do? Well, we ran a mechanical Turk experiment. And by that, I mean Jael ran a mechanical Turk experiment where she sat down and she came up with a bunch of instances that look a lot like this of multi-winner approval voting, where we're going to pay we're going to pay respondents accordingly to whether or not they can get their preferred candidates to win. So they're paid based on the outcome of the election, which means that they're sort of incentivized to cast votes that maximize their expected return. So we had 104 participants recruited through Mechanical Turk. We had sort of a first condition, and then that branched into two separate conditions at the end. So half did a condition 2 with a 2 winner, half did a condition 3 with a 3 winner, but everyone did the condition 1 with the 1 winner. So we have 104 people that did the 1 winner condition, and then 50 and 54 because the random number generator was weird. So participants are going to vote in scenarios with, we tell them there's either 0, 1, or 3 missing ballots. This is to look at, especially in the heuristics literature, how uncertainty changes what heuristic you may select. That's what they were trying to tease out of this data. You could vote for as many candidates as you wanted. We had a little pretest. We screened off some people who submitted garbage the whole time. We did sort of the normal Amazon Mechanical Turk data cleaning type of things. And everyone was paid as compensation in proportion to how much they sort of got as part of their voting. And so inside of our conditions where we modified 1, 2, and 3, everyone did a little bit with the uncertainty. We also had setups for these. These were all sort of carefully constructed by Jael to understand 5 different scenarios. One would be something like a neutral leader, where the leader of the election was worth $0, but there was a chance, depending on if you cast your ballot properly, for your most preferred candidate to win through either the tie-breaking rule or to win outright. We had this trivial candidate model, which was where this is an example of trivial candidate. Sorry, this is a trivial leader, excuse me. Trivial candidate's leader is still 0, but the chance for the most preferred to win, as well as one with low pay. So this would be sort of a trivial candidate. The trivial leader, where the leader is a low payout, which is this one, but it's possible to elect a high value candidate if you want to. One, which we'll see in a bit, where the dislike candidate, there's a candidate with negative utility that can win, and so you have to manipulate your manipulate your vote. And also a no-win scenario where there's little to no chance of any candidate that you want to win. And so what we did this before is because we wanted to sort of look at how the preference distribution that the decision makers saw maybe affected the way that they made decisions, how the number of winners, it's the K, right, changes possibly that, or the amount of uncertainty, how they respond to one of these 3 factors. And again, in the next couple of slides, you're going to see comparisons to 3 heuristics. I'm going to swap the word truthful in here for complete for the moment, just because we changed terminology between papers because we got yelled at. But we didn't update the slides, so I didn't get to that. So when you see truthful, just think complete. Take the X best is the same. We also looked at a regret minimization heuristic in the first paper to see if people were maybe making decisions based on regret minimization in the face of uncertainty. So given how many votes there were left to cast, were they trying to sort of think through how to minimize their regret based off of the way that those votes came in? And so what we did was we went through and we computed the expected utility, which is just the expected payout, and the corresponding best heuristic to use for every possible number of missing votes and every possible number of winners. This was just brute force, right? We have the setting, we just generate all the ballots and compute it. And so in the neutral leader, where the leader is worth 0, but there's a chance for the most preferred to win, you see this has kind of got this weird thing where you're better off being truthful or voting with complete ballots for part of the time, but also there's a setting where you want to maybe just take the best 2. If you look at the outcomes that people actually did, only about 21% of voters voted optimally across all possible conditions. So we tracked each voter and to see if they were making the optimal decision basically at every point that they could have. Very few people did that. You do see that a lot of people, especially in this condition, just submit truthful votes, which is kind of interestingly, correct for a lot of the settings. And then if we sort of break this down by the percentage of participants using the strategy, you'll see that it seems like in this 3 winner sets, people start using take the 2. They still vote truthfully, even though take the 2 best is the best thing for them to do. So you get a lot of non-optimal behavior here, but you see a lot of people sort of just voting truthfully. I'm going to probably speed through these a little bit because I want to make sure I have time for the second part. So I'll point out some fun stuff though. So in the trivial candidate, again, leader 0, but chance for the most preferred to win. You'll see this changes the heuristic that has the maximal payout a bit. In this one, you do see a little bit more, a few more people really optimally, but you see a lot more take the X best, right? A lot fewer truthful when we give them something that looks like this, where they maybe just need to cast a ballot for E. And they're really, I think, take the 1 best really kind of dominates. You'll see that a lot of here. Because what they're doing is they're just picking E to try to get the 1 best, and that works for a few of these, but it's not really the optimal thing to do when there's a lot of missing votes. Okay, there seems to be a duplicate of that slide. Oh, so the fun part, just for fun, for those of you who were at the Dogstuhl in 2019, back when we could still travel, there was a pilot of this study that we ran with everyone who was at the Dogstuhl on applications-oriented social choice. And so I dug up the results of that, and I wanted to ask myself the question yesterday, did the voting experts do better than the people on Mechanical Turk in terms of doing what was optimal? And the answer, I mean, just off the top, is yes. So the voting experts were about 20% better at selecting the optimal strategy across all possible conditions. So I was really hoping it went the other way, just so I could make a joke today, but it turns out that the voting experts did actually do it better. And you see a lot more reliance on this take the X best strategy. Perhaps it's not surprising that people that study voting manipulation and things like that as part of their job, we're pretty sure that truthful was not the right strategy to go with. So take from this what you will, but I thought it was funny, little side note. So trivial leader, again, we're still getting only about 20% of optimal. You're seeing really heavy reliance on take the X best as these get slightly more complicated. In the dislike candidate scenario where we've got a negative $1, it's really a lot of regret minimization that you're trying to do. So you'll see a lot of votes for just the candidate with the highest payout. You're just trying to do something to make sure that this guy with a negative $1 doesn't win. And you do see a lot of people sort of moving into this regret minimization framework, but a lot of people do fall back on just voting truthfully. Finally, in the no-win scenario where there's 2 candidates that are worth $0, there's a very small chance if you cast a truthful ballot with 3 missing votes that you'll end up with the you'll end up with the highest payout. And you do see people sort of able to figure that out. When there is no chance, they usually either abstain or they do what's in the heuristic literature called like a follow the leader. They just sort of vote for one of these 2 guys because they're already winning. So they're just like push them over the top. Which is kind of interesting. So the conclusions from the Turkers, or the big takeaways here, is do people vote using, if you want to ask the question, do people vote using a maximizing strategy? Do they actually vote optimally? The answer is mostly no, right? You see really less than 50% across all conditions of people voting in the most optimal way. Do people vote truthfully or do they vote completely for all candidates with positive utility? Again, mostly no. They do tend to vote sincerely. And they tend to use some variant of take the X best, where X is the number of winners in the election. And if you go through and sort of boil down all the data, you'll see that in 1 winner elections, they really do do take the X best with one winner. In 2, they do take the X best with 2. And in 3, they do take the X best with 3. So very often you're seeing that heuristic where they're using the X as being the K, and they'll only vote for exactly that number. And there was a few of the conditions where it was optimal to vote for more or less, but you'll still see this really strong reliance on K. And it's not clear if that's like a priming effect or what's going on there. But it's kind of interesting, right? Because that seems to be the heuristic that we're all using. So do people change their strategy depending on the amount of uncertainty? And again, this was the most surprising thing, is the answer is no. So people saw the same question with 1 missing vote, 2 missing votes, and 3 missing votes, and was staggered so that it wasn't right next to each other. But you'll see them vote the same across all the conditions, even with more missing votes. And we're not sure, obviously we can't tease out if that's they didn't read the directions very well, or if that's actually something that's happening behaviorally. So in our last 4 minutes here, we're going to turn to see if we can model this voter behavior using some sort of model that's a little bit better than these just straight heuristics. All right, so we're going to zoom in, and we're only going to focus on two of the settings that we use. I'm going to call this top one A for the moment, and the bottom one B. So this is the trivial candidate, and this is the trivial leader, right? So again, here, trivial candidate means there's a 1 cent and a 0 cent, and it's kind of asking, are you indifferent between these two things? And you'll see actually that almost 70% of the voters are really using a take the X best here. We're getting about 20% voters to vote optimally across these. And one of the reasons that we're using these two is they have the same heuristic sort of mapped onto the same settings, right? So it's a little bit cleaner to do some of the data analysis. So that's why we sort of zoom in on these two just for this part. So sort of a brief reminder, 90% of the ballots were sincere here. Voting behavior didn't change significantly between the two scenarios, or is the amount of uncertainty increased. What you do see in these fun, stinky alluvial diagrams is that you'll see as going from 1 winner to 2 winner, and again, 1 winner to 3 winner, you'll see a lot of moves from take the 1 best to take the 2 best, or take the 1 best to take the 3 best. And you'll see where we go from having a take the 1 or 3 best here, or take the 1 best here, over to take the 3 best in this 3 winner condition. So you see a lot of change in the behavior when the number of winners increases. And so this is what sort of led us to think, well, it's got something, people are responding to this number of winners, and they're doing something with this in order to think about what they want to do. And so what we went to is there's this attainability utility heuristic for plurality voting, which was developed by Fahrenstein and Reshef and a group. It built on an older paper that looked at just the attainability heuristic for sort of 50-50 voting. And this is, I think this T shouldn't be here. Sorry, this is slightly the wrong equation. But what it's trying to do is it's looking at a trade-off between the attainability of a candidate and the utility you have for that candidate as well. This was originally developed for single winner elections, and there's a little bit of finagling we had to do to get it to work for multi-winner elections, mostly because it's built off the number of candidates available and the number of ballots that you know, and the distribution over the ballots that you don't know. So you're kind of looking to trade off how likely is it that the voter that I like wins. And you're using this exponential mixing between the two to say, okay, if there's no chance for him to win, then it doesn't really matter, right? So attainability and utility are combined in this product form, and they're weighted by this alpha. So it's sort of saying, like, if I like somebody good enough, then it doesn't matter how unlikely it is that they will win, I'll still vote for him. But if it's very likely that somebody wins, you know, they were kind of going to mix these two things together. So we had to, this was originally developed for binary choice. Fahrenstein et al. Extended this for plurality elections. We had to do a little bit more finagling to make it work for multi-winner approval voting, because it's dependent on the number of ballots that you expect to see. And in approval voting, you have this weird thing, right? Where if there's 1 missing vote and 5 candidates, that could be sort of 1 ballot, 2 ballots, 3 ballots, 4 ballots, you know, any kind of number of ballots. And so you have to modify this. If you take it in a straightforward way, if you modify it in sort of the straightforward way, it's kind of asking you to do this exponential average over all the possible ballots that you might see, right? So you're thinking about all the ballots that people might cast, and you're trying to do something with that, which seems, as soon as we showed this to Jason, Jason was like, that's not how people think, that's too complicated. So we should do something else. And so again, I'm kind of breezing through this because I have just a couple of minutes. It involves, like I said, sort of modifying this equation to take into account how many possible approvals could arrive And one of the reasons that we need to do this is you take the normal attainability utility model from the Fahrenstein paper, it actually will never predict anything besides a complete ballot because of the way it's designed. So if you sort of jam the numbers in there, it'll always give you something that looks like a complete ballot. It won't actually give you what people are doing, which is some sort of version of take the X best. So this is kind of a justification of why we need to modify, even with this modification that we did to bring it into the multi-winner space, its prediction space is not encompassing all the behavior that we're seeing. And so what Jael ended up sort of working out is that probably what's happening is people are using some sort of thresholding model. And so she added this threshold to the equation. It's built into the this A sub beta score. And what it's doing is it's only looking at utilities or attainability within a certain threshold, given how much I think that the candidates are going to do for me. And so what it does is it sort of makes these levels of prediction that people are going to go through. This expands for various settings of T, the prediction space, so that we actually get this take the X best strategy again as part of the outcome of this model, which is what we wanted. And so then we did sort of a leave one out. Oops, forgot to put a title here. We did a leave one out prediction with the scenarios that we have. So for every individual voter, we had 6 ballots. We tuned the parameters on 5 of those and we predict the 6th. We did leave one out. So we do these all the different ways that we can to get some confidence bounds. We run this. What we kind of end up seeing is that our AUT, right, our attainable utility with threshold, ends up predicting that left one out ballot significantly more than all these others, except for sort of take the K best and the 3 winner, where K is always set to 1 winner, 2 winner, or 3 winner. So what we kind of get out of this is that our model does much better at predicting the ballot that's observed within group. So for each person, we are working on some across group to try to say something more at a population level. That might go to a journal at some point, so maybe somebody will review it. And that's sort of the whole paper. So I'm happy to talk more about it. Again, we performed these real world experiments to understand how agents actually make decisions in multi-winner approval voting, and understand what heuristics actual decision makers are using, and then develop new heuristics for those users as well. And so with that, I will stop because I think I'm right at about 20. And I think I had one question already in here. So
before we go to the question, I would like to ask for a major round of applause from everyone. Unmute yourselves and clap frantically into the microphone. Yes, there was a question by Bill in the chat already.
If I was using a variable threshold, EO, vote for all candidates with utility above the mean utility, would you detect that or classify that as something else? That is a good question, Bill. That's something that we talked about. We didn't actually do it, and we didn't think about it beforehand. So we haven't done that analysis. My concern, I'll talk to Jael and see if we can go back and do that. My concern would be that the thresholds that would be for a bunch of the experiments, because the payouts are fixed across almost all the experiments, like the sum payout, so that way we could control how much people were getting paid. So it might not change very much across the conditions that we tested. So it's a good idea, and it's something we thought about, I think, afterward, but I'm not sure if that's going to be useful from the data we have, just because of how we constructed the elections that we used to do this experiment. Because we wanted them all to have the same average payout, so it was easier to compute, like, what the range of payments were. Because for the IRB, we had to guarantee that we were paying these people above a certain amount per hour and stuff like that. So it was a little finagling of that kind of thing.
One of my thoughts is that in the future, an experienced group of approval voters might behave differently than your random sample here, because some more sophisticated heuristics might be available for them to learn about.
Yeah, and that's why I wanted to dive more into the Dogshell data, but I didn't really get around to it until about the middle of this week. So I didn't have enough, and it wasn't formatted the same way, so I didn't have enough time to really like dive into that. And it's also like 17 people versus about 105. So
yeah, then go to the, I don't know, Caldita, you want to ask yourself, or is it?
Yeah, I just thought, I think this is very interesting. And one of the reasons is that in many municipal elections in the United States, you actually have a required vote for K or fewer. So if there's a certain number of at-large seats on a city council or a school committee, it is approval. So you can vote for as few as you want, but you're not allowed to vote for more than the total number of seats available. And I was curious if you had any thoughts about the kind of whether you'd be able to acquire real life data about this, that you could use with a model, or whether in principle, it seems like your data is indicating that even if you give people a full approval, they might just say no more than K. I'm just not going to do. And that's, to me, that's interesting, since that's what's actually implemented in a lot of real life elections.
Yeah, so that's a good question. I think we might have one or two in PrefLib that are some from these municipal approval based elections. That's an interesting, I should go in there and run it. But my guess is for some of them, I wouldn't have the number that they ran with. So what the K set would be. But you're right. It is interesting that people seem to fixate when you tell them there's going to be 4 winners, they vote for 4 people. When they tell them there's going to be 1 winner, they overwhelmingly vote for 1 person. So it does seem kind of, at least from a behavioral standpoint, that people are responding to this in some way that's kind of interesting. I guess they do this for the city council elections just to force you to be decisive in some way. Like if everybody was just casting full ballots, then it wouldn't.
Well, the really weird where we are, we actually have a primary system where in the primary, you also get to vote for up to the right number of people. And then they take twice that many to get into the final election. Why twice? Why not 3 times? Why not 1.5? But if there's 4 seats available, there will be 8 people in the final.
You gotta have a good slate. I don't know. That's interesting.
Okay, Peter.
Peter asks, does the missing vote model entail that the voters have information about nearly all of the votes by others? So, Peter, what they're given, just to let me make sure you get the right idea here. So we give them, they see this picture, right?
Yes.
One that looks like
and
this.
I was wondering what the picture means.
So it's the number of votes so far, right? So we tell them there's been 3 votes for candidate A, there's been 3 votes for candidate B, 4 votes for candidate C, 3 votes for candidate D, and 3 votes for candidate E. And then in the uncertainty setting, we tell them, we tell them basically there are 2 voters left to vote, or 1 voter that will come after you. So someone else will arrive and vote after you. And this is after they've done a little bit of screening to say, so that we make sure that they know that, if they vote for candidate A, like this will go up by 1. So they go through a little tutorial on approval voting before they start.
Okay, but that seems a rather non-standard way, because if you have a real life election, you don't have any information at all about how the others vote.
Right.
So
we don't tell them,
under
we don't
that
tell them.
condition, you would expect that voting for the maximum number of people you approve at all would be anyhow optimal due to lack of information to the contrary.
Yeah, the thought process that we were going through, there's a fair bit of work on voting with pre-election polls and things like that. So that's why we gave them the votes ahead. And because we went through a couple different questions of how to model uncertainty. So there's other work that we didn't do that other people have done, looking at, if you've got a poll and you tell people that it's like, there's a margin on these polls and things like that. And Jason and Jael sort of decided that it made more sense for the ease of this experiment to sort of say the uncertainty is modeled as, exactly what's coming in, you don't know what's going to happen after you. So you're making a decision at a point where you're not sure what's going to happen afterward. And that apparently maps a little bit better onto these cognitive heuristic type research in the psychology literature.
Okay, so that explains a point which I missed during the talk. So it was a more explanatory question. Thanks.
No problem.
Do we have any further questions? Maybe a final one. If not, that's also completely fine. I think we had a very satisfying session with lots of questions overall. So thank you very much once more, Nick. That was great.
Thanks, y'all.
So then let me say one more time what's going to happen next. So we're going to take a bit of a break now in the seminar for the next almost 2 months, and we're going to come back in September. And from September onwards, for the foreseeable future, we expect to have 1 session per month. And we expect that usually to be the 2nd Thursday of that month. So that would mean that on the 9th of September will be the first session. It will be at the usual time of the day. We haven't entirely fixed the speakers yet for that session, so we'll announce those speakers on the website when we know who they are, and then you'll get an email in the week of that seminar. And the idea is by announcing that we usually think it will be on the second Thursday of the month, that people can kind of try to keep that free in their schedule. I mean, I hope that some of you at least will have the chance to have seminars in person again. And in case it's going to be on a Thursday afternoon, maybe not the second Thursday of the month, and then we get the best of all these very many different words that we live in. All right, thank you very much. Those of you who will have a summer, please do enjoy it. And the people who are going skiing, like Harris, I guess, please enjoy that as well. And I see you all in September. Bye-bye.
Thank you.
Thanks, Ulle. Thanks for organizing.
Thanks all.